Alright, so this is problem 7 out of Kenneth Crane's Modern Physics textbook. Before we get started, go ahead and subscribe to the page and like the video. That'd be really great if you could do that for me. And yeah, let's go ahead and get started with the video on how to solve this one. So it says the proper lifetime of a certain particle is 100 nanoseconds. Question A asks, how long does it live in the laboratory if it moves at a speed of 0.960 c? Okay. So the first thing I'm going to do is just go ahead and do a quick conversion. So delta T naught, that's your proper lifetime, is 100 times 10 to the negative 9 seconds. Just converting nanoseconds to seconds. And we know the speed. That was also given in the problem. Okay, so if we want to know how long does it live, well, then we can use our time dilation equation, which is this. The proper time times this factor, the square root of 1 minus v squared over c squared. And we have all this information. We have delta T naught in seconds. We have our velocity. So all you have to do is plug that in. And when I did that, I got 3.57 times 10 to the negative 7 seconds. So that's all that one is. That's pretty straightforward. You just have to use your time dilation equation there. Part B wants to know how far does it travel in the laboratory during this time, and C wants to know the distance traveled in the laboratory according to an observer moving within the particle. There's actually a few ways to do this. There's one where you can use length contraction, but I think the easiest way is just knowing which time to use in each reference frame. So for example, for part B, we want to know how far in the laboratory does it move. So if you're observing this from, I guess you could say, the outside looking in, we could say delta L, the distance, is equal to rate times delta T. Now, why are we using this and not the proper length and proper time? The proper time would be if you're moving with the particle. So for part C, we would actually use our proper length and our proper time. So that's all we need to do. The velocity, the direction will change, because if, let's say, the particle is moving in this direction, it would look like the laboratory is moving in the opposite direction from the perspective of the particle. You can think of that as like if you're driving along in a car and kind of looks like everything's moving behind you, but really you're moving forward. But it's really dependent on your perspective. But that's kind of how I usually think in terms of a car driving, because that's the most real world experience I think we have. Anyways, delta T was given to us, or it wasn't, but we actually just found it right here. Delta T naught was what was given to us, and we have the velocity. It helps that just make sure that this is in seconds, because this is 0.960 times c, which is 3 times 10 to the 8 meters per second. So don't use nanoseconds in this case. We want this to have units of seconds, which it already does, but just in case you didn't convert in the beginning. And if you plug that in, you should get 102.816 meters. Now for C, it's the same thing. Instead you're going to use delta L naught equals V times delta T naught, which this one was given in the equation. And again, we already converted that. It's the same idea with our units here. And if you plug this in, you should get 28.8 meters. So really, it's just kind of helping you get your bearings. I think this question is good for helping you get your bearings correct for what is proper length, proper time, versus just delta L, delta T. And if you know that, it's a very easy problem to work through. So hopefully that helps. I'm going to continue working through these. And yeah, please like,